Hello there and welcome to the series of videos going through the content of A-Level Maths. Here we're looking at projectile motion formulae, so we can answer questions from exercise 6D. So it's roughly doing the same sort of maths we've done in exercise 6C, only this time we're just going to be doing it with algebra. There are about 4 or 5 different things that you need to be able to show using algebra. For some people it does make it a little bit more difficult, but really it's just all the same maths that we've looked at in 6C. So let's get started on the question then. So a particle is projected from a point on a horizontal plane with an initial velocity u at an angle of theta above the horizontal and moves freely under gravity until it hits the plane at point B. Given the acceleration due to gravity is g, find an expression for the time of flight, the range of the horizontal plane, and it's just those two parts there. So first of all, let's draw a clear diagram so we can visualise the question then. So we've got an initial speed u at an angle of theta degrees, and it's going to be projected and it's going to launch upwards and then start to head downwards after a while. So first things first is to resolve the initial speed. So we're going to have u cos theta along the horizontal axis, u sine theta along the vertical axis. And now we can start to have a look at the time of the flight. So for the time of the flight, we need to either consider whether we're going to work in the horizontal axis or in the vertical axis. Now for the horizontal axis, we don't actually have the distance that it's travelled horizontally, so it would be very difficult for us to work out the time that it's travelled horizontally. But when we look vertically, we do have the distance that it's travelled vertically from starting point to end point. It's travelled a distance of 0 vertically. Well, it's not travelled a distance of 0, but its displacement is a distance of 0 from start point to end point. Yes, it's travelled upwards and then downwards, but the displacement from one point to another is 0. So in this case here, we're going to be resolving vertically. I'm going to set upwards as positive. So s, the distance of the displacement from one point to another, when we look only vertically, is 0. It's from this position here to this position here. It's not moved in that vertical dimension. The initial speed vertically was u sine theta. V we're not really interested in. A is the effect of gravity, that's the acceleration due to gravity, that's minus g in this case. And then finally t is the value we're looking for, so we'll just leave that as the value t. So what we'll do then is we'll delete v and we'll now look for an equation that links s, u, a and t together, and that is s equals ut plus half at squared. So write out the formula, substitute the numbers in, so we're going to get 0 equals u sine theta for u, t is just t, and then it's plus half, the acceleration is minus g, and then t, that's just t. So what we'll do then is we'll tidy that up a little bit and then we'll factorise out the value for t. So now effectively here what we've got is we've got a component here where either t is equal to 0, or we've got the whole of this bracket here that will equal 0 instead. So therefore just rearranging this and then working out what t is, double both sides, divide by g, and then we then get t equals 2u sine theta all over g. Lovely there, so it's the same kind of maths that we've been doing in 6C, only we're now doing the whole thing with letters and the whole thing with algebra. So yeah, there we are. For some people it makes it more difficult, but you're still using the same strategies. For part B then, the range of the horizontal plane. Well, we know that the time that it's going to take from this point here to this point here is going to be the time of 2u sine theta all over g. So we can use that in our calculation for the horizontal distance. We can use horizontal suvat here, or actually what would probably be easier is because the velocity is not changing, we can just use distance equals speed times time. So therefore the horizontal speed, that's going to be this speed here, and then it's going to be the time of the flight, which is equal to what we've just worked out in part A, 2u sine theta all over g. So then put that all together and we get 2u squared sine theta cos theta all over g. And then we simplify 2 sine theta cos theta, that can simplify to sine 2 theta. So therefore the range then will be given by this formula here, u squared sine 2 theta all over g. Lovely, so there we are, that's the answer to that question then. So same kind of maths as I've said before, all we're doing then is we are just doing the whole question with algebra. Okay, so moving on to a tricky question here then. A particle is projected from a point with speed u and an angle of elevation theta and moves freely under gravity. When the particle has moved a horizontal distance x, its height above the point of projection is y. Show that. And now we've got a really difficult formula here. It's in terms of x, and it's dependent upon the values u and theta, the initial speed and the angle of elevation, as you would expect. So in this type of question here, we're going to be working in both of the directions, both horizontally and vertically, to get to the intersection of that kind of coordinate x, y. So the first thing we'd do, obviously, is set out a diagram: horizontal speed u cos theta, vertical speed u sine theta, and we're going to be intersecting a point x, y effectively. On the horizontal axis, it's going to have a displacement of x, and on the vertical axis, it's going to have a displacement of y. So the first thing we're going to do then is we're going to find the height in terms of t. So that's effectively the value for y. So resolving vertically, taking upwards as your positive direction. So the displacement for the particle when it reaches this coordinate xy here is y. That's the distance that it will travel upwards. The initial speed is u sine theta in the upwards direction. V we're not really interested in. Acceleration will be going downwards, and that's due to gravity, so minus g. And t is what we're looking to find. So we need to think of a formula that links s, u, a and t together. So that's going to be s equals ut plus half at squared. So substitute the numbers in, you're going to get y equals u sine theta times t plus a half of minus g times t squared. And what we've got now is y equals ut sine theta minus a half gt squared. Now it's starting to resemble what we're trying to show here. We just kind of need to get rid of these t values here, and then hopefully it will tend towards that expression there. So we're kind of halfway there really. We now need to look in the horizontal direction. We want to intersect this coordinate x, y here. So therefore when we start to resolve our velocities in the horizontal direction and work out distance equals speed times time, we're going to be using a distance of x this time. So horizontal distance equals speed times time, and we're looking for horizontally how we get to x. So substituting the values, the horizontal distance that we would like to travel is a distance x meters. The horizontal speed, we resolve that as u cos theta, and we don't know how long we need to travel in this direction for, so we'll just leave t in there as the value for time. Now what we can do now is rearrange this thing here and substitute the answer into the t value for the y equation down there. So divide by, okay, let's set out all the equations then. So divide by u cos theta, so we get x over u cos theta is the value for t. And now it's going to get substituted into the equation for y. So replacing t with x over u cos theta, doing it very carefully, so it's going to be u times t, which is x over u cos theta, times sine theta, and then minus g brackets x over u cos theta, and that's all going to be squared, that part there. Okay, hopefully what we're going to do now is expand the brackets and end up with what we're looking to show here. So let's go ahead and expand the brackets now. So for the left-hand expression, we're going to have ux, sine theta will be on the top, and it will be u cos theta on the bottom. And then for the right-hand expression, we'll just square everything inside the bracket, so it's going to be x squared, u squared, and cos squared. So, cancelling out the u's for the left-hand expression, simplifying sine over cos to tan, so we get y equals x tan theta. Then we're going to have for the second part here minus g x squared over 2u squared, so kind of just pulling some of this stuff out of the brackets, and then it's going to be 1 over cos squared. Now we know that 1 over cos squared is just going to be sec squared, but we don't want sec squared in our final answer, we want this 1 plus tan squared, and luckily 1 plus tan squared is equal to sec squared exactly. We can show that by the sine squared plus cos squared equals 1 identity. So using the trig identity at the top of the page there, we get our final answer. Lovely. So a really challenging question here. It involved working both horizontally and vertically, rearranging for the time, and then substituting the time into the equation that we worked out for y, and that's how it came out. Lovely. So a difficult question there. But still exactly the same methods as we've been doing in 6C. Okay, this is now an example of how we can use these formulas in a question here then. So a particle is projected from a point A on a horizontal plane with initial speed 28 meters per second at an angle of elevation theta. The particle passes through point B, which is 8 meters above the plane and a horizontal distance of 32 meters from A. Find the two possible values for theta, giving your answer to the nearest degree. Now, generally this would have been a part B question to the part A question that we've just completed before. We can use this formula here, we've just calculated it effectively in the part A of this question, so now we can start to substitute values in. We still don't know the value for theta, so we're going to leave theta in there, but we do know the value for the initial speed is 28, we know the value for x is going to be 8, so we know the value for y is going to be 8, and we know the value for x is going to be 32. So taking this formula then and substituting in the values we know, 8 is the value for y, x is the value 32, don't know what tan is, g is 9.8, x is 32, u is 28, and we don't know what theta still is. So we can simplify this now. And we're going to get a large quadratic, try and get rid of fractions where possible, and move everything onto one side. Now you can either pull out the quadratic formula here or go to the menu button on your calculator, option A I think it is for the polynomial solver, and type in these values here. And it looks like we're going to get two values for tan. So substituting it into the formula, tan theta is either going to equal 0.5 or 4.5. So then, we now know, just before we get started on this question here, we know that our angle of projection is going to be somewhere in between 0 to 90 degrees. That's kind of assumed in our question here. We're not going to have a 132 degree angle, because that would be firing the missile backwards effectively, firing the projectile backwards. So we're only going to be having angles in between 0 to 90 degrees. So just quickly doing the inverse tan of these values, we get 27 or 77. No need to go searching for other values in this case. So, thinking about why there might be two different possibilities here for it to intersect 8 and 32. Well, what could effectively happen is if it's looking to intersect this point B here, then it could have intersected point B on the way up effectively, or it could intersect point B on the way down. So that's the reason why we have two values here. So we've got a summary of the formulas that you could be asked to show here. Now please do not go back and memorize these formulas off by hand. You need to know how to get to them using the methods of resolving velocities and then doing vertical suvat and horizontal distance equals speed times time. So you need to know how to get to them rather than memorizing them off by heart. And that's exactly what I've explained there. So then, our turn to have a go at a question then. Pause the video and try this question out. Okay, so a particle P is projected from a point with initial speed of 21 meters per second, so U here is 21, at an angle elevation of alpha and moves freely under gravity. When the particle has moved a horizontal distance x, its height above the point of projection is y. Show that y equals x tan alpha minus x squared all over 90 cos squared alpha. So you need to be able to do these without memorising the formula that you've already had. So, if we remember, let's draw ourselves a diagram of what's going on here. we have a horizontal plane, an initial speed of projection of 21 at an angle alpha, and it's going to be projected, launch upwards, and then head back downwards, and it's going to intersect a coordinate x, y. It's going to travel a distance x on the horizontal plane, and at that point it will have travelled y meters upwards. So in this case then we need to, if we remember the technique for doing this, it's to resolve our velocities first. So it's going to be 21 cos alpha, and this one here is going to be 21 sine alpha, and then it's to do suvat vertically and do distance equals speed times time horizontally and combine the two times together. So we remember the method rather than memorizing the formula. So first of all, resolving horizontally for suvat, we're going to have s equals the distance of the height upwards will be y. The value for the initial speed going upwards is 21 sine alpha. V we're not really interested in. A is minus g, and t is actually what we're going to be looking to still keep in our formula, but then get rid of it later. So we're going to use s equals ut plus half at squared. So that's going to be 21 sine alpha times by t, and then it's going to be minus a half g because it's a plus half a t squared. Okay, so that's the vertical equation. We now need to get something for the horizontal equation. So when it's travelled a distance x, its speed will have been 21 cos alpha at a certain point in time. So we're going to be doing distance equals speed times time here, the distance being x, the speed being 21 cos alpha, and the time being just t. So we can rearrange this into t equals x over 21 cos alpha. Let's now go ahead and replace this in this formula here to get our final answer. So y equals 21 sine alpha times by t, which is x over 21 cos alpha. And that looks promising because the 21s will cancel out and we'll be left with a tan. Great, looks like we're on the right track so far. Then it's going to be take away a half times g times all of this thing being squared. So I'm going to write x squared over 21 squared cos squared alpha. So we've got the cos squared alpha on the bottom, we've got the x squared on the top. What I'm kind of hoping is that all of this half times g times 1 over 21 squared will simplify to 1 over 90. Let's just do a quick check of that on the calculator. 0.5 times 9.8 divided by 21 squared, and we get 1 over 90. That's great. That is exactly what I was looking for. So then, final answer, cancel out the 21s, then simplify sine over cos is equal to tan. So x tan alpha minus, and then the half g over 21 squared simplifies to 1 over 90, so it will simplify to x squared over 90 cos squared alpha. Great, so you're memorizing the method to do this rather than the value, rather than the equation that you can just substitute in. It's difficult to tell whether you'd get full marks if you memorize the formula and substitute it in the values, so don't risk it, do it by the method. Given that y equals 8.1 when x is equal to 36, find the value for tan alpha. So the first thing we've got to remember is that cos squared can be simplified, so 1 over cos squared can be simplified to sec squared, which can also be simplified to 1 plus tan squared. So it's going to be 36 squared over 90 times by 1 plus tan squared alpha. So then simplifying our fractions here, we're going to have 8.1 equals 36 tan alpha minus, and then it's going to be 36 squared divided by 90, which is 72 over 5. Write that as a decimal, 14.4. And then it's going to be that times 1, and then it's going to be that thing times by tan squared. And then let's just move up into this space here. So then simplifying everything onto one side, we're going to have 14.4 tan squared alpha. And then we're going to have a subtract of 36 tan alpha. Trying to form a quadratic here, moving everything onto the left-hand side. And then it's going to be 8.1, add 14.4. So that's going to be 22.5. So add 22.5. Great, okay then. So last thing to do then will be to put this into your polynomial quadratic solver. So grabbing your calculator then, and it's going to be typing in the values. 14.4 times 2.5 divided by 2 times 14.4. So our answer here is going to be tan alpha. Whoops, tan alpha. We're probably going to get two values of tan alpha. Is 5/4. And we're also going to get 5/4 as well. It perfectly factorizes into 5/4 and 5/4. It'd be a repeated root here. Lovely, great. That would probably mean, I'm not sure what that would mean. Anyway, there we are. We get 5/4 for the value tan. Excellent. So hopefully that was helpful. Answer all the questions from exercise 6D. It's quite a difficult topic, this, so the more practice you're going to get, the more familiar you'll be able to jump into questions quicker and be more efficient with your time. So do practice a lot of questions here, practice all of the problem solving ones, the exam style questions, and ask your teacher for help if you need any. Great, thanks very much for watching.